Hey mechanics students, welcome to a pool party. Oh, it's so great. I thought I'd throw a pool party in celebration of talking about torsion. Oh, I just love torsion, and nothing's greater than getting out in the outdoors, getting some sun, and thinking about how things twist and the angle twist and their shear stress and all that good stuff. So let's see what we got for our learning objectives today. So we got number one, we want to be able to plot torque diagrams. So like we did axial force diagrams for one-dimensional bars under axial loads, we're going to draw torque diagrams for one-dimensional bars under torsion. Secondly, we're going to develop the equation for shear stress due to torsion and the equation for the angle of twist. Next, we'll explain and calculate polar moment of inertia. And finally, we'll apply the torsion formula and the formula for the angle of twist to solve some engineering problems. All right, so we want to get started and talk about torque diagrams. So let's think about torsion as we apply it to this pool noodle. When we plot the torque diagram for a member, it's important that we're plotting the internal torque to that member. So what's happening on the inside of the material. And so this is much like we do for shear moment diagrams as well and for our axial force diagrams. So in our example, we have a wall and we have the rod fixed at point A. And then I come over to point B and I apply a counterclockwise torque. Now that's counterclockwise using the right hand rule down the x-axis. So I apply a counterclockwise torque. What is my torque inside this member? I think we can see that the torque throughout the member should be counterclockwise. I want to show that to you by coming up with a free body diagram. What about my reaction? My reaction has to be clockwise, right? Because it has to resist my applied torque at point B. And so I have a clockwise torque here at the fixed wall at A, and a counterclockwise torque at B, and we'll draw some free body diagrams to see what kind of forces are going on the inside. So hopefully you can see the parallels between the pool noodle example and this example shown here to get our sign convention for the internal torque. So when I apply a counterclockwise torque at B, I get a clockwise torque at the support at A. When I talk about counterclockwise and clockwise, I'm using the right-hand rule with the x-axis shown. So counterclockwise is positive using that right-hand rule. Now, when I plot the torque diagram, I need to plot the internal torque inside the member. So whenever we go to come up with the internal forces, we always make a free body diagram of a cut. So let's go ahead and circle, and we made our free body diagram, and now I've sketched that free body diagram below. Inside, I have the torque at A, that reaction torque is still existent. And then on the surface of my cut material, I have a torque acting counterclockwise. And this must be true for equilibrium. This counterclockwise torque is the internal torque in this particular member. And again, if we use the right-hand rule, we consider that counterclockwise motion is going to be positive. And so I would sketch the torque diagram as having a positive value of T, or whatever the torque is here at point A, and at point B it's the same magnitude throughout for this particular example. Whenever I sketch these diagrams, I like to include my sign convention directly in the diagram. So you see here I'll say that this torque is positive, and positive means counterclockwise, and since I have my x-axis shown, I know that it's counterclockwise using the right-hand rule about the x-axis. When plotting torque diagrams, I find it easiest if we just set some basic rules that we can follow. So as we move down the x-axis, if we have a clockwise applied torque, then our torque diagram will jump up. And if we have a counterclockwise applied torque, it will jump down. Now that might seem a little bit counterintuitive, but remember, our torque diagrams plot the internal response of the material. So when I have an applied torque that is clockwise, my member, the resistance of my member has to be like a counterclockwise shear stress to resist, a counterclockwise torque to resist my applied torque. And so it's that positive kind of counterclockwise internal torque that I'm plotting on my diagram. And so this is kind of like when we have point moments, when we look at a moment diagram and we have like an applied point moment. Remember, an applied point moment that is counterclockwise causes a negative shift in our moment diagram, whereas a clockwise applied moment causes a positive shift in our moment diagram. So it's kind of analogous to that if you remember back to moment diagrams from statics class. So, all right, so go ahead and write down those rules, and then we'll go ahead and apply them later when we look at some of the torques in the problems. So here we just want to capture those rules. So we said that whenever we have a clockwise torque that's applied, this causes a jump up in our torque diagram. So if you look at our example above, starting at x equals 0, so at the fixed support, we have a torque A that's clockwise, and so that causes a jump up in my torque diagram. And then when I get to the end of the member at the cut, or if I look at the top picture with torque at B, when I get to the end of the member, that counterclockwise causes me to jump back down again and return my torque to 0. Again, it all comes down to the sign convention and just remembering that we want to plot the internal forces, or like the internal response to the applied loads. And so if we go back to statics and we talk about point moments, remember if we applied a couple point moments like this to our cantilever and we had a fixed end moment that was counterclockwise as shown, this actually causes a negative jump in our moment diagram. And then a clockwise applied moment causes a positive shift. And so again, that shift is a value of m1. Remember, it doesn't jump all the way up to a value of m1, but the shift is m1. And so I've kind of used the curly brackets there to indicate the shift. We'll be doing the same thing when we draw torque diagrams. We'll be kind of moving along the length and then jumping up and jumping down using the magnitudes so that we can sketch the torque along the entire length of a rod.